This is Prestvarnet near Tromsø. It is a frozen lake on a hill, on an island, in a strait, around 350 kilometers north of the Arctic Circle. But the most interesting feature here isn't part of the geography at all. It's part of the sky. This far north, we are well into the auroral zone. That is, the belt around the Earth's northern geomagnetic pole from where the northern lights are most visible. Which is why, just over there, you can find the Norwegian Centre for Space Weather, a joint research facility of the Arctic University of Norway and the Norwegian Space Agency. Aside from sounding rad as heck, space weather research has some very important ramifications. Solar activity can interfere with satellite navigation services like Galileo, which is used for navigating ships and aeroplanes. It can induce dangerous electrical currents in long metal structures on the Earth's surface, like train lines. In humans, it can increase your likelihood of suffering from cardiovascular health problems and may even affect our mental health. It's difficult and important work. But for me and many other visitors to Tromsø, one of the most exciting things to come out of the space weather research here is this: a forecast for the Northern Lights. The Northern Lights, or Aurora Borealis, are multicoloured waves of light that can be found dancing across the night sky in northern regions. They have a southern counterpart, the Aurora Australis, which is typically limited to Antarctica, but can be seen as far north as New Zealand, South Africa or Chile. The aurora have been referenced in human folklore for thousands of years, from Australia to China to here in Norway. But it wasn't until the 20th century that we could explain them with science. On Earth, we are familiar with three states of matter: solid, liquid and gas. However, on the surface of the Sun, temperatures around 150 million degrees Celsius cause electrons and atoms to separate, creating a fourth state of matter, which we call plasma. It's easy to think of the Sun as a smooth ball, but in reality, it's more like the stormiest sea you can imagine. High temperatures and intense magnetic fields can accelerate plasma to speeds of several hundred kilometers per second. A small proportion of these particles reach high enough velocities to escape the Sun's pull altogether and go flying off into space. Scientists call this the solar wind, which honestly sounds misleadingly relaxing for a supersonic stream of highly ionizing particles. Most of these particles are deflected safely off the Earth's magnetic field, but a few are captured and drawn in towards the poles where they enter the atmosphere and collide with gases. These collisions give a lot of excess energy to atmospheric gases, which they release by emitting electromagnetic radiation, in this case, visible light. The exact colour of light produced depends on two factors: which gas is being collided with, and how much energy was transferred in the collision. For example, collisions with atomic oxygen in the upper atmosphere will produce a red light, whereas collisions lower down in the atmosphere, which involve more energy, will produce a green light. It does get more complicated than this. For instance, nitrogen is actually quite stable, so can often hang on to its excess energy for long enough that it will collide with something else and pass it on. However, the general principle that excited atoms will release energy as light is pretty much the same way as how neon lights work. So how can we turn this knowledge into a forecast? Well, for one, we know that stronger solar winds and other space weather events will send more plasma our way. This can sort of be predicted by studying solar cycles, which repeat every 27 days. However, the best short-term forecasts are based on data from remote sensing instruments in space. On an annual timescale, we can consider how the Earth's magnetic field aligns with that of the solar wind. Imagine taking two magnets and lining them up. If they're both facing the same way, then their magnetic fields will reinforce each other, acting like a single, stronger magnet. If you then flip one of them, their magnetic fields will cancel out. Well, pretty much the same thing happens as the Earth orbits the Sun. And around the time of the equinoxes, that is in March and September, the north-south component of the Earth's magnetic field is more or less the opposite to the Sun's magnetic field, which is carried by the solar wind. This biannual event, known as the Russell-McPherron effect, weakens the Earth's magnetic field meaning that more solar wind can make it into the atmosphere and the northern lights shine brighter. Of course, there's never any guarantee that you'd be able to see the northern lights. Even if the space weather is perfect, then Earth weather can still get in the way and completely block your view. However, if you put yourself in the right place and you're patient enough, then you might just get lucky.